hardest shot in bowling is the 7-10 split. To knock down both pins, the ball has to collide in such a way that one pin ricochets into the other. Amazingly, by trying to knock down one pin, it leads to the collapse of the other. In math, we build theorems that often have immediate implications. But some of the rarest and most beautiful proofs are the ones that pop out of nowhere through the solution of a seemingly unrelated problem. I hesitate mentioning this proof technique now because you haven't learned all the basic proof techniques. Describing this proof technique is the mathematical equivalent of trying to explain irony.
Isn't it ironic? Don't you think?
But this is indeed the trick that we use to prove Cauchy-Schwarz. We derive this inequality by solving the geometric problem of finding the point on a given line that is closest to the origin. The prototypical example of the 7-10 split is elliptic curves and Fermat's last theorem. But I make it a policy to never talk about anything I can't prove.
Idiota maduro.
Guess I'd make a pretty lousy politician. Instead, we could look at a theorem you will prove in 52H. Recall in Calculus BC, you used P-series to prove that the sum of 1 over n squared from 1 to infinity converges. But what does it actually converge to? Using the entirely different subject of Fourier series, the answer magically pops out as pi squared over 6. There are a lot more fantastic examples of the 7-10 split. My personal favourite is proof of codes. A proof of code solves the problem of storing data structures known as trees. But we can also use it to solve a seemingly unrelated problem. The problem of counting the number of labelled trees with n nodes. However, these examples involve words you've never seen before, like trees and Fourier series. But you came here to do math. You want to see theorems that you can understand. So here is an example from your Algebra 2 days. The binomial theorem tells us how to expend a power of a binomial. But we can actually use this to prove set theoretic facts. First, we define. A set A is a subset of a set B if, for every x in A, x is also in B. Often, this expression will be denoted by A subset B. Alternatively, we can write B is a superset of A. The first set theoretic property we will prove is that any set of size n has 2 to the n subsets. For example, the 3-element set 0, 1, 2 has 2 cubed subsets, namely 0, 1, 2, 0, 1, 0, 2, 1, 2, the set containing no elements, and the full set 0, 1, 2. As you will see, this is an easy application of binomial theorem. Any set of size n has 2 to the n subsets. To summarise the proof, we will first expand 1 plus 1 to the n using the binomial theorem, and then interpret the right-hand side as the number of subsets. Proof. Plugging x equals 1 and y equals 1 into the binomial theorem yields 1 plus 1 to the n equals n choose 0 times 1 to the n times 1 to the 0 plus n choose 1 times 1 to the n minus 1 times 1 to the 1 plus n choose 2 times 1 to the n minus 2 times 1 to the 2 up to n choose n times 1 to the 0 times 1 to the n. This simplifies to 2 to the n equals n choose 0 plus n choose 1 plus n choose 2 up to n choose n. But how do we build all the subsets of an n-element set? The number of ways to build a subset of size I is simply the number of ways to choose I elements out of the original n elements, or n choose I. So the number of subsets of an n-element set is n choose 0 plus n choose 1 plus n choose 2 up to n choose n. But this is the right-hand side of our previous equation. We can also use the binomial theorem to prove that any set has an equal number of odd and even size subsets. In our previous example, 0, 1, 2, the number of even-sized subsets is 4, whereas the number of odd-sized subsets is also 4. Any set of size n, the number of odd-sized subsets is equal to the number of even-sized subsets. This time, we will expand minus 1 plus 1 to the n using the binomial theorem. Then we will move all negative n choose I terms to the left side of the equation. Finally, we interpret one side as the number of even subsets and the other side as the number of odd subsets. Proof. For ease, let's assume n is even. The argument for n odd is essentially the same. Plugging x equals minus 1 and y equals 1 into the binomial theorem yields minus 1 plus 1 to the n equals n choose 0 times minus 1 to the n times 1 to the 0 plus n choose 1 times minus 1 to the n minus 1 times 1 to the 1 plus n choose 2 times minus 1 to the n minus 2 times 1 to the 2 plus n choose 3 times minus 1 to the n minus 3 times 1 to the 3 up to n choose n times minus 1 to the 0 times 1 to the n. This simplifies to zero equals n choose 0 minus n choose 1 plus n choose 2 minus n choose 3 up to n choose n. Moving all the negative terms to the left, n choose 1 plus n choose 3 plus n choose 5 up to n choose n minus 1 equals n choose 0 plus n choose 2 plus n choose 4 up to n choose n. But this just says the number of odd-sized subsets is the same as the number of even-sized subsets.